So hi everyone, and welcome to an instrumentation class. In the previous class, we spoke about op amps, noise, how can we eliminate noise, feedback a little bit, bandwidth, and the effects of bandwidth on the signal. And I realized after the class was over that part of the audio wasn't recorded, so I have to record that and upload that again. Today we will continue with feedback and the control systems in a measurement and instrumentation system. I would also continue with the benefits of feedback, a little bit about the measurement tools and type of errors that we have. We will speak about scale, error, drift, and if we have time, we would speak about mean and standard deviation. Depends on how can we cover today. Now, what is feedback and why do we need feedback? For those who had the linear integrated circuits with me, we saw that feedback is a necessary part of an op-amp amplifier. And the reason that we use that feedback is to make the system stable and to have control over the amplifier's gain and the output. Most systems that we have usually have a feedback system, especially if we have a control system. And the feedback is mainly to have some sort of control over the output. So in some measurement systems, if we want to have control, we need to have feedback. And the feedback, the topography is usually like this. We have a system, which is a plant process, and then from the output of that, we get a signal. We put it through the feedback path, and which could be a controller, and then we feed it back to the system, to the input. Now, some examples of feedback systems are industrial process controls. So in some manufacturing processes, integrated circuits, for example, temperature must be closely controlled. We can do that using a feedback. One example of using a feedback system is in your HVAC system, the thermostat that you have at your home. That has a feedback. There are different types of feedback systems. Usually when you are doing temperature measurement and temperature control, there is a type of feedback system called the PID. I don't know if you're familiar with the PID feedback, but in control system, you would see that PID is a very popular type. Sorry, my pen stopped working, but PID, it's the integral differentiator type of feedback that we use and control systems that we use. I don't want to get into the detail. This is a topic for control systems, but there are different type of feedbacks and control systems that we can use to control the temperature. Now, this is the topography, stopped working, of a temperature control system. We will set the desired temperature using our thermostat here. Let's say we want to put our house at 70 degrees Fahrenheit. And then that is usually to the control system, which is our thermostat. And what it does, we have a sensor here that measures the temperature of the house. And let's say the temperature of the house is 68 degrees Fahrenheit, and our desired temperature is 70 degrees. And what it does, the control system sends a signal to the furnace and tells the furnace to turn on and increase the temperature. The temperature starts rising until it reaches usually 71 degrees. Usually it's 1 or 2 degrees above the desired, or if it's in summer, it's 1 or 2 degrees under that, or half a degree or 1 degree. And the reasons we don't want to continuously, turn on the furnace. We wanted to give it like 10-20 minute rest So it depends on the application and what type of thermostat you're using. If it's an industrial and you want to precisely, control temperature, we usually don't do that. If it reaches 70 degrees, it turns off. But if it's in a home, it usually has like a 1 degree overshooting. And then when it reaches this, it sends the signal to the control system, and the control system turns off the furnace. Again, when the temperature senses that it's dropping below 70, let's say 69 degrees or 68 degrees, it turns the furnace back on. Now, if your home only has one thermostat, usually the temperature sensor is on that thermostat. But if there is a big, home, if you have a big home or a school or something like that, usually we have multiple sensors distributed around the house or a school, and they pick the temperature because obviously if the temperature sensor is close to one of the, vents, or if it's close to a door, it will record a different temperature than the average temperature of the house. So the best way is you put multiple temperature sensors and you get an average of that, and then you decide to turn on the furnace or not based on that. And the newest thermostats, they have multiple sensors. One is usually on the thermostat, and one you have the furthest from the furnace itself. They could communicate wirelessly or with wire, but usually they do it wirelessly on Wi-Fi or Bluetooth. And we have what we call a mesh network. And then the control system can decide based on that. And newer thermostats, I don't know if some of you may have the Nest at your home or Ecobee or one of these what they call smart thermostats. They also have a motion sensor in them. And what they do is if they detect that there's no movement in the house, they would automatically drop the temperature. And they have like a away from home, option as well that you can select. And if it doesn't detect any movement in the house, it would automatically let the house temperature to drop, let's say to 65, 64. So it would, reduce your energy consumption. So you can add multiple sensors to this. Some temperature sensors, thermostats, the smart ones also they would directly connect, like the Nest, they would automatically connect to, they are connected to internet, so they would pull weather data as well. So if it sees that today is going to be a sunny day, it would turn off the furnace early in the morning because it knows that the temperature will get up eventually. And some of them even have sensors like I've seen other types that have outdoor sensors as well that could measure outdoor temperature and adjust indoor temperature according to that. And again, you can read faster than I can. The control system sets the current supply to the heating elements in the furnace to keep the material temperature at the desired or set point value. Another example is a car cruise control, which is a feedback system. Now, how does it work? You have a sensor, which is speed sensor, which is on the transmission, for example, measures the car or the object's speed by measuring the rotational speed of the tire. And then you have a set speed, which is the cruise control. You can put it at 75 miles per hour. And then if the car is going faster, it's going down a hill, it will put on the brakes. If it's going slower, it put on the gas, and increase the speed. We also have adaptive cruise controls nowadays, which is a radar, and you can set the distance between these two as well. That is also a feedback system. We have another type of system which we call a feed-forward system as well. A feed-forward system is a type of system that is used, for example, in a Mercedes. The camera can see ahead and see if there is a pothole or something like that, and it will automatically adjust the suspension to go over the. So what it does is actually it softens the suspension, so you have a more comfortable ride. So we have feedback, feed forward. Feed forward is used in some applications, but mainly we would use feedback. Now, some benefits of the feedback, it makes the system stable with respect to the changes in system parameters. It helps to obtain a nearly linear response from nonlinear components. It can be used to change the characteristics of a system under control. Now we have two very famous feedback systems, the integral and the derivative system. The derivative, as you know, calculates the slope. So any small changes is rapidly responded. Integrator measures the area under a curve, so it's like smoothing and averaging a system. Okay. So integration is very good when you have noise, and differentiator is very good when you want to have a fast response. Now, the classification, again, I don't want to go deep into that. That's a topic of another, like control system and also signals and system class. But if you want and you're interested, you need more information, just stop by my office and I would explain more about that. Now, the classification of instruments, we have the absolute instruments and secondary instruments. Absolute instruments are instruments that give the magnitude if the quantity under measurement terms of physical constants of the instruments. The secondary, these are calibrated by the comparison with absolute instruments, which have already been calibrated. So absolute is also the primary. Sometimes they call it primary instruments as well. And these are what we call the benchmark or the gold standard for the measurements. Now, sometimes we can't use absolute instruments. We use the secondary instruments that are cheaper, easier to use. So for example, if a factory is building a digital multimeter, DMM, they need to calibrate the voltmeter to an absolute instrument to be able to measure the voltage accurately. Depending what application we use, if we want a very high-end instruments with very high accuracy, we need to calibrate it using these absolute instruments. If you need a mainstream multimeter that you don't care about, if it's very accurate, like 1-2 volts is not going to make a big deal, you can calibrate it using secondary instruments. Now further, it's classified as deflection type instruments and null type instruments. Now, functions of instruments and measuring system can be classified into three, and they are the indicating function, the recording function, and controlling function. Applications of measurement systems are monitoring of a process and operation, control of process and operations, and experimental engineering analysis as well. So one example of an indicating function would be a monitor that you add to an Arduino, and it just shows the temperature, but it doesn't have any memory, therefore it doesn't record any data. You can add a 7-segment or a LCD display, and it just shows you real-time data. The next step is to show the data and record it, so you need to add a memory. So if you add a memory to an Arduino, you can record that data, for example, temperature as well. And the most complicated one is that you can show it, you can record it, and you also can control a function. Same thing that we had with a thermostat. If you have a thermostat at your home, it displays the temperature. It sometimes records it, sometimes it doesn't, but it can control a function which is controlling the furnace as well. Now, in terms of intelligence, we have two types of instrumentation system. We have intelligent instrumentation, which the data has been refined, and sometimes we can pre-process or process the system, we get rid of noise, and do some decision on that. And then we have DOM instrumentation. That data must be processed by the absorber. One example of intelligent instrumentation I can give you is an MRI device. An MRI device, what it actually the device sees is it measures magnetic fields, and it must do a lot of process. Actually, the MRI device itself, it has maybe the size of 2 or 3 of these rooms just filled of computers doing the processing side. It's a very complicated device. So you can't even process that raw data. It's very complicated. And a DOM instrument could be as simple as a voltmeter that you measure the voltage and you see it, and the operator decides if it's, so for example, if you're measuring the outlet voltage and you see the voltage, it's 100 volts, and you know definitely there's a problem with that outlet. Or it's 200, 220 volts, then you know it's a single phase, it's going to be a problem. So you have to interpret and analyze that data. And there's a lot of different examples for that as well. The MRI is a very, very sophisticated and advanced system. So another example of an intelligent instrumentation system would be as simple as the thermometers that you use, like a child thermometer, and it just gives you like a red light, a blue light, or a green light that shows if someone has a fever. So it automatically analyzes and determines if the fever is above 104. It shows you like an alarm or something like that. So it must be able to, again, process the data as well. Now, elements of generalized measurement systems, we have and this is important. You may have a quiz on this. We have primary sensing elements. We have variable conversion element. We have data presentation element. Now, a primary sensing element, the quantity under measurement makes its first contact with the primary sensing element of a measurement system. So it's a sensor transducer. And we have the variable conversion element. It converts the output of the primary sensing element into suitable form to preserve the information content of the original signal. Can you think of a variable conversion element? So the primary is going to be the signal, the sensor itself, or a transducer. Can you think of a variable conversion element that converts that output? So imagine you have a sensor that measures voltage. It's a continuous signal that is measuring voltage in real time. What can a variable conversion element be after that? Yes, yes. So an analog to digital converter could be a good example for that. And you're getting analog data, converting it to digital to be able to process it or store it. And yeah, the cruise control one could be an example as well. And then we have the data presentation element, which the information about the quantity under measurement has to be conveyed to the personnel handling the instrument or the system for monitoring, control, or analysis purposes. Again, this could be as simple as an LCD monitor, or it could be a control system, a computer, a microprocessor, or a microcontroller that makes decisions based on that data. Now, this slide shows the functional elements of an instrumentation system. You can see that the primary sensing element, which is the detector transducer stage, this is the sensor, and which measures the quantity that we want to be measured. And then we have the intermediate stage, which is the variable convergence elements. It could be a filter for eliminating noise, an amplifier, and also an A to D converter. We have the variable manipulation element, and we have the data transmission element. Again, this could be a coding if you want to transmit data and if you want to code it. So you want to do a secure transmission of data, that could be done here as well. Or if you just want to compress the data to be able to easily transfer that without using a lot of bandwidth. And then finally, we have the data presentation element, which is the transmitting stage. Now, some static characteristics of instruments and measurement systems. Application involved measurements of quantity that are either constant or vary slowly with time is known as static. And then we have, for the characteristics, we have the accuracy is important, drift, dead zone, static error, sensitivity, and reproducibility of the system. We also have other characteristics. This is just some of them, such as the static correction, the range, span, noise, dead time, hysteresis, and linearity. These are other characteristics, and I would explain about each of these characteristics. And on the first exam, I would say 20% of the questions that you have are related to these characteristics. Now, the first characteristic that we have for these instruments and measurement systems is accuracy. You're all familiar with it. Accuracy is the measurement of the closeness of the actual or true value and the value that the instrument reads. For example, if we have water and we want to measure how much water that we have in a tank, and the tank has some, indicator scales on it, and it says it's 1 gallon. And then we have a sensor, like an ultrasound sensor, that measures the water in the tank. And that ultrasound sensor shows us 1.1 gallon. So we know that the actual value of volume of water in that is 1 gallon, and the measured value is 1.1. So the accuracy is in 0.1 of that measurement. Another example, if you want to measure the temperature, and you know that the temperature is 45 degrees Fahrenheit, but the instrument is showing us 46 degrees. So we know that the accuracy is in about 1 degree Fahrenheit. Obviously, the more accurate the device is, it's going to be better. We want something that is super accurate, but it comes with a cost. Usually, devices that have higher accuracy, measurement tools that have higher accuracy are much more expensive. And sometimes you have to make them much more complicated to be able to measure a high, and to be able to measure with high accuracy or have a highly accurate system. Sometimes we don't need a very accurate system. An example would be the thermostat in the house. We don't care if the temperature is 70 or 71 or 70.5 or something like that, because that 0.1 or 0.2 doesn't make a huge difference. But if you want to make a decision on a medical decision using an, biomedical instrumentation, a huge error, a small error makes a huge difference. Let me give you an example. And this comes back to sensitivity and specificity and accuracy. These three are very important in medical diagnostics. And let me give you an example. In medical, we have something we call the true negative, true positive, false negative, and false positive. What does this mean? True negative, it means that, for example, imagine we have a test that determines if someone has COVID or someone has cancer. True negative means that we know that this person is healthy and truly the result of that, exam or this COVID test is negative. Okay? True positive means we are 100% sure that this person has this disease. Like this test that came out at the beginning of the pandemic, And some of them, the true positive rate was like 99%, meaning if the result came out positive, you were 99% sure that you had the disease. But the true negative was like 70%, meaning if you got a negative result, you were 70% sure that you didn't have the disease. But there was a 30% chance that you had the disease, but it showed negative. And that's called the false positive. And then we have another thing called false negative. So it means that you make a test, false positive like 40, and you know that this must be a false result. There's a 40% chance. Now, some companies were a little sneaky about this, meaning that their true negative was 60% and their true positive was 95%. Meaning, if you did a COVID test and the result came out negative, there was still a 40% chance that it was positive, and this was showing false negative. Does that make sense? So technically, you did the test. If you still were negative, you may still have the COVID. So the recommendation to everyone was you get the test. If it still shows negative and you have the symptoms, it's probably you have the disease, and you have to do the precaution. So it's not a very accurate system. Accuracy comes out actually as true positive plus true negative over false positive plus false negative plus true negative plus true positive. So again, accuracy is true positive plus true negative. Let me write it down, the equation. So accuracy in a medical condition is actually equal to true positive plus true negative over false positive plus false negative plus true positive plus true negative. Now, this is a better indication. When you are calculating the accuracy, if they say the accuracy is like 99%, meaning there's a very low chance that you get false positive or false negative, for example, because these two should be very close to zero. So this would be close. If these two are zero, you're going to have something that is close to 1 or 100% accurate. Okay. There is a matrix that it's called the confusion matrix. It's like this, and that matrix shows false negative, true positive, true negative, and false positive. If someone is interested, I would, provide more information about that. But in medical term, and this is very important, imagine someone goes and does a test for, let's say they do a PET scan for a cancer or an HIV test, and you tell them, and the result comes back that they have 90% chance, or they come back that they have HIV, they are HIV positive or cancer positive. But the test, that has a true positive rate of 90%. So there's still a 10% chance that that person doesn't have that disease. So you need something that is very close. Anything actually below 95% in medical term, it's not very accurate. You have to be very, very sure about something, okay? Now, some of these at-home tests, like glucose monitoring tests, they are like 92% accurate. Let's think of another test, like pregnancy tests. They are very high, like 99, 98%. So some tests, if the testing result, or at-home tests for, colon cancer, or there's a lot of tests, those are not very accurate. There's are actually accuracies like 85, 86% accurate for those. So because they usually look for blood, and if there's not a trace of blood, the person may still have, colon cancer, for example. These are some examples that I'm giving. So this, in medical terms, is very important. You need very high accuracy. But if you're measuring a room temperature, it's not going to be very important. So lower accuracy is acceptable there. I hope I haven't confused you, but accuracy, again, sometimes not important. When you are doing a medical diagnostic, like cancer diagnostic, that becomes very important. That's the reason they do they do an MRI, and then they do a PET scan, and then do a biopsy, because they want to be 100% sure that this person has the disease or not. They don't just rely on a simple, blood test. Yes.
If you were going to calculate the accuracy of something and say it's, like a 70% true positive, but the values that you plug in be 70 for the TP, and then false positive would be 30?
It's not as simple as that. That's a great question. You may think that true positive would be 70 and this would be 30. It's not like that. You may have this as 70%, this as, this one as 60% as well. So it's not as simple that you think, oh, because this gives me a 70% true, it's a 30% false. It's not that. We have another graph for that. It's called the ROI. And I could share more information about that, but it gets very complicated, when you get that. Again, I'm going to write the same thing that I had here. So accuracy is equal to true positive plus true negative over the same thing that I draw on the board, over false positive plus false negative. So if you do a search, what we call a the confusion matrix. And if you look at it, this is actually what a confusion matrix looks this. And the reason that it calls it confusion because it confuses everyone, I think. So even the doctors, and you can see that it can get very complicated when you have a true positive situation. And if you go to actually Wikipedia, you can see the equations for specificity, sensitivity, and so on. So for sensitivity, and these are the equations for it, by the way, you can find it for sensitivity, meaning how sensitive is the test is how sensitive it is and how specified it is. And sometimes they measure what they tell sensitivity and specificity with prevalence as well. And if you go down here, there's a lot of information. I think you can find the equations for yes. So accuracy, as I mentioned, sensitivity, specificity, all of that you can measure, you can calculate all of that using the difference equations that you have. Like this is an example of a cancer system. This is the predicted condition and actual condition. Actual condition means the true value, and predicted means what we have measured. So the absolute value and the predicted value. Okay. Now the other thing that we have is called the true value. The true value of quantity may be defined as the average of an infinite number of measured value. So the true value means the real value of that. For example, if someone has cancer, that's the example. But the problem in the real world, we can never know what the true value is because we have to measure it at some point. So a good way to know the true value is to measure something thousands of times, of infinite time. Some example is you want to know the true value of the temperature of this room. The only way to do it is to use 10 different sensors and measure it 100 times and average that so you would know the true value. So don't rely on one sensor, do it with 100 sensors, very 100, So if you average that on infinite number of time, that's going to be a true value. Sometimes it's very difficult to do that. Then you have the sensitivity, which is defined as the ratio of the magnitude of the output response to that of the input response. You want to see how sensitive it is. Again, the magnitude of the output to the input, or the true value to the measured value, you can say. Another characteristic is called the static error. It is defined as the difference between the measured value and the true value of the quantity. So for example, if our temperature is, the true value is 76, and the measured value is 78, then our static error would be 2 degrees. AM is the measured value and AT is the true value. It is also called the absolute static error as well. So in an exam, if we ask for absolute static error, it's also the static error, the difference between the measured and the true value. Now, another characteristic is called the scale range. The scale range of an instrument is defined as the difference between the largest and the smallest reading of the instrument. So if you have a voltmeter that can measure between 5 volts and 200 volts, the scale is going to be between 5 and 200. In other words, 200 minus 5, it's going to be 195. It's going to be our scale span. So again, if you have a voltmeter that can measure between, let's say, 10 volts and 200 volts, then your scale range is between 10, I'm going to call it SR scale range, and 200. Now, why is scale range so important? Perfect. Thank you. Yes, so you don't blow up your instrument. Imagine you have a furnace, you want to measure the temperature, it's melting, aluminum. You can't measure it with a, mercury temperature sensor. You can't even sometimes put a thermocouple in it. It's going to just melt it, a physical. You need to measure it from a distance using an infrared, thermometer, something like that. So scale range, when you want to measure something, you have to make sure that the instrument is capable of measuring that. Another example, if you want to measure a high voltage, you can't use a voltmeter that it's up to 250 volts, and you want to measure something 1,000 volts. It's going to be, first of all, it's going to immediately destroy your measurement tool. Second, it's going to be sometimes very dangerous as well. And then we have the scale span. The scale span or instrument span is given as the scale span, which is the difference between the upper limit or the highest value that it could measure minus the lowest value that that device could measure. So it's the difference between the highest and the lowest point. So for the previous example, the scale span is going to be equal to 200 minus 10. It gives us 190 volts. Now, another characteristic is going to be reproducibility, which is specified in terms of scale readings over a given period of time. We want our measurement device to be able to reproduce the results day in and day again. Meaning if I measure the voltage of this room, the outlet in this room, and it shows me 120 volts, if I measure it in the afternoon, it should show me 120. If it's in the morning, in the winter, summer, it must be the same. And one example of this that I gave you already was the ultrasonic sensor. Do you remember I talked about the ultrasonic obstacle sensor that you have on your car? The problem with these sensors is that if you measure a distance in the winter, it's going to be different from summer. If you do it in Amarillo, it's going to be different than if you do it in DC or in Houston. Because these measurement tools depend on the environment. Environment has a lot of impact on them: temperature, humidity, even altitude, so air density, all of that have. And sometimes that's causes a problem. Imagine you want to measure, imagine you want to measure a voltage in a grid, and the instrument shows a different results in cold weather compared to hot weather. Therefore, you don't get the accurate reading that you're looking for. So that's going to be a problem. Another problem with the characteristics of this measurement instrumentation is drift. Drift is an undesirable quality in industrial instrument because it is rarely apparent and can't be maintained. We have different type of drifts. We have zero drift, we have span drift or sensitivity drift, and we have zonal drift. One example of the drift is this. Imagine we have a spring that we use to measure somewhat we use it in a scale to measure weight. And we would attach a weight to this. Let's say this is 100 pounds or so. What happens if I use the scale over and over again for a year? What happens to the spring? Yes. So the spring, what happens if I put too much weight on it? After a while, it stretches, and it doesn't go to its original space. So if it should go back to 0. After a while, when you stretch this, it doesn't go back to 0. It goes back to, let's say, 1 pound or something like that. Okay. This is called a zero drift. And it happens a lot, especially in electromechanical sensors like a voltmeter. They have a spring, and the problem with these springs, when you use it a while, the spring loses its characteristics. It doesn't go back to 0. It stretches, and you put too much stress in it, it does that. So what you have to do, they usually have a knob on them that once in a while, you have to correct it and recalibrate it. And this happens for a lot of measurement tools. Even I have seen this, what we call a CBS tools. So the tools that they have in the labs for measuring, doing a blood work, measuring glucose, or cholesterols or something like that, they have to be calibrated every day because they have drift. Meaning when you test 4 or 5 blood samples, it creates a little bit of drift because the sensor itself becomes a little bit contaminated, or you have electric pulses, and a lot of different problems causes drift. The way that we could fix these drifts is to recalibrate. So if you forget to recalibrate these devices, it will show measurements that are not true, inaccurate. Sorry. Just give me a second. Pen stopped working. Okay. So since we have a small pause, do you have any questions up to now? No? Okay. Now, the things that we spoke about were static characteristics. Other characteristics of measurement instrumentation systems are the dynamic characteristics. Some of these are, 1, the speed of response, measuring lag, fidelity, and dynamic error. So already you may know what the speed of response is. In measurement tools and instrumentations, we want something that is rapid, fast, and gives us rapid response. Imagine you have a radar, adaptive cruise control, and it measures the distance. It takes 2-3 seconds. By the time the reading is done and given to the ECU of the car, you already crashed into something because it takes 3 seconds to read the distance, and if the car in front of you stops, it doesn't realize and it crashes. So sometimes we need something that is super fast and rapid to response. And again, speed of response is the speed that the measurement actually does a measurement after the quantity of that value has changed. Again, we want something that is very fast. Sometimes we don't care about the speed that much. Like, again, as I mentioned, temperature of a room. We don't measure temperature of the room every millisecond or nanosecond. We measure it every 5 or 10 seconds. Sometimes we actually want to preserve energy. That's the reason we have intervals, like measuring a temperature every 10 minutes or so. And now we have fidelity. Fidelity, it is defined as the degree to which a measurement system indicates changes in the measured quantity without any dynamic errors. Now, what is a dynamic error? It is the difference between the true value of the quantity changing with time and the value indicated by the measurement system if no static error is assumed. It is also called the measurement error. So if in the exam I ask what is the measurement error, is actually the dynamic error. It is a dynamic characteristic of a measurement system. Then we have the measuring lag. It is the retardation delay in the response of a measurement system to change in the measured quantity. It has two types. We have the retardation type, which the response begins immediately after a change in measured quantity has occurred. And then we have the time delay. The response of the measured system begins after a dead zone after the application of the input. And I've seen a lot of that, and you may see a lot of these too in your project as well. That we have a dead zone. It takes some time for the system to turn on. Even the microcontroller, there is a delay in the sensor itself. Sometimes you have a delay in the microcontroller. So you have a very fast sensor, but the microcontroller takes time to convert that data from analog to digital, process it, and then display it. That's the reason sometimes you need a very fast processor. A 40 megahertz microcontroller may not work. You need something that is faster. Now, some errors in measurement systems. We have the limiting errors or guaranteed errors. We have the known errors. And the classifications are that we have gross errors, systematic or cumulative errors, random or residual accidental errors. Now, the systematic or error could be the instrumental or environmental or observational error. Now, some examples of gross error are human mistakes in readings, recording, and calculating measurement results. Their experimenter may grossly misread the scale. For example, they may read 31.5 instead of 21.5. This is human error. When you're reading, person doesn't put their glass on, or they're tired and they misread, the measurement. Or instead of reading, for example, they may have a transport or reading error as well, which they will read 25.8 example instead of 28.5. Now, the way to counter this error is to do multiple readings. So we would ask the person to read the value every 5 minutes or every 2 minutes, or read it 3 or 4 times. Okay, that's one way to get rid of it. Or have 2 persons read, so someone to check and double check. Same thing that someone does when they do a blood test. They use second opinion or repeat it sometimes. And then we have instrumental errors. These arise due to 3 reasons. Due to inherent shortcomings in the instruments. So you have a cheap, low quality instrument. Due to misuse of instrument, the instrument falls, and now you don't have the mechanical shock has significant impacts on some instrument tools. And sometimes it's due to loading effects of the instrument. One example is, again, you measuring a value that it's over its scale, and then it causes drifts in the system and errors in the system. And then we have the environmental errors. These errors are due to conditions external to measurement device. These may be effects of temperature, pressure, humidity, dust, or of external electrostatic or magnetic fields. The ultrasound is a good example of that. And then you have the observational error. The error on account of parallax is the observation error. Now, another type of error that we have is called the residual error. This is also known as residual. The error is due to multitude of small factors which change or fluctuate from one measurement to another. The happenings or disturbances about which we are unaware are lumped together and called random or residual. Hence, the errors caused by these are called random or residual. So you may have, for example, a multimeter that has multiple errors, small errors. Some errors come from temperature, heat. Some comes from magnetic fields. We don't know the exact source, when you move the device, it doesn't show that error. This is type of a resist error, and some comes from hysteresis error as well. Now, a good way to be able to mitigate and eliminate error is to do the measurements multiple times. And when you do it multiple times, we want to get the mean, and that average is going to give us a true value or a better representation of that measurement. So some mathematical terms that we use to eliminate error, one of them is going to be averaging or mean, arithmetic mean, which you are familiar with. It's the most probable value of measured variables. The most probable value of measured variable is the arithmetic mean of the number of readings taken. It is given by this equation, x bar, or the average of x, mean of x, is going to be x1 plus x2 plus xn. So all your measurements divided by the number of measurements, number of times that you did it, or number of readings, which is going to be equal to sigma x, or n, where n is the arithmetic mean, and x1, x2, x3 is the readings of the samples, and n is the number of readings. Another thing is deviation. You're already familiar with it. Deviation is the departure of the absorbed readings from the arithmetic mean of the group of readings. So D1 is going to be x1 minus the mean or average. D2 is going to be the reading x2 minus the mean or average. D3 is going to be x3 minus mean. Dn is going to be xn minus mean. And when you add all these deviations together, it's going to result in a 0. Another factor that we have is called the standard deviation. A standard deviation of an infinite number of data is defined as the square root of the sum of the individual deviations squared divided by the number of reading. So standard deviation, sigma, is going to be equal to square root of sigma d square over n if the observations are above 20, and if they are 20 or less, sometimes the 20 or above is used above equation. It's going to be square root of sigma d square over n minus 1. Please write this down because I'm going to give you a practice problem on this now. Now, the variance is the square root of, the standard deviation square, or standard deviation in the power of 2. In other words, variance is going to be equal to sigma d square over n. This is for observations above 20, and for observations below 20, variance is going to be sigma of d square over n minus 1. Now, let's solve a problem. We have 10 observations recording a voltage, and the 10 observations are as follows. First one is 41.7, second is 42, third is 41.8, 42, 42.1, 41.9, 42, 41.9, 42.5, 48.8 volts. We want to find the mean, standard deviation, and probable, I skipped the probable error. By the way, probable error of one reading is 0.6745, and the probable error of mean RM is going to be R1 over n minus 1. Going back to the question. Okay.
So that R1 is a set value?
Yes.
It's always 0.6745.
Yes. Yes. Yes, yes. R1 is 0.6745. And N is the number of readings that we have. Here is 10 readings. The important part, I want you to find mean and standard deviation and range if you can. By the way, range is the difference between the lowest and the highest. So if you want, I can go back to the standard deviation equation. Is this? It's going to be D1. So you have to first find the mean, and D1 is going to be mean minus the first reading. D2 is going to be mean minus the second, and so on. And finally, standard deviation is going to be sigma of D squared over N minus 1 because the reading is less than 20. Okay, does anyone have the answers? Yeah, what does it mean? Huh. Yes, okay, very close, okay. And what is the standard deviation? Perfect. This is what I will calculate, 41.97, pretty close. So. Do you have 41.9? Okay. And the standard deviation is 0.22, and probable error is 0.15, and the range is 0.8 volts.
Can you explain how you got the probable error real quick?
It's R 0.6745 over 10 square root of 10 minus 1.
Yes, but I've plugged it in a couple of times and I keep getting 0.225.
225. So it's probably, yeah, maybe I've done maybe it's, yeah. I have to double check my calculation, but maybe that. What about the range? Did you get the same for the range? Yes, okay, perfect. So this one, double check this one. Again, maybe yeah. And the important part was the mean standard deviation in the range. Now, calibration is an important part of all instrumentation tools. Since it affords the opportunity to check the instruments against a known standard and subsequently to find errors in accuracy. And the calibration process involves a comparison of the particular instrument with either a primary standard or a secondary standard with a higher accuracy than the instrument to be calculated or calibrated with. And the standards is a physical representation of a unit of measurement. The term standard is applied to a piece of equipment having a known measure of physical quantity. Again, in these factories, they usually have a calibrated standard system that they can measure against that and determine its accuracy. Types of standards, we have the international standards defined based on international agreements. We have the primary standards maintained by national standard laboratories, and then we have the laboratories, and then we have the secondary standards used by industrial measurement laboratories. So this is it for this lecture. You can find the references as well. I just want to mention something, and we have a small quiz before that. Just want to bring something up. Just give me a second to see if I can find it. Yeah. Okay. For those who are interested in doing a final project using PCBs, I've already, in additional resources, I've already added the EasyADA project link. It's a great resource. Please watch the videos, and it's a great way to learn how to do PCB boards. There is a website, EasyADA. It's free. It's web-based. You don't have to install anything. You can install it as well on your computer. It has a tutorial step-by-step how to do a PCB board. And also, it's connected to a JCBL. It's a company that you can directly, after you're done, it creates a Gerber file, and you can directly send it there. The first few PCBs that you print, it's going to be free. They just charge you a shipping cost. And then I've added another one, Arduino Masterclass. For those who are not familiar with Arduino, I would highly recommend that watch this class. It's like 90 minutes. It goes through everything. And another one is the ESP32 Node MCU. That's IoT based. I've put it here for those who are interested in learning more and for their final project. I would highly recommend that you go through these two. You may have a question on this on your homeworks, and it's going to help you again with your final project. I would recommend that you start with the final project right away and get used to Arduino and also PCB design. It's going to help you on all your courses, senior design, circuit design, and so on. Thank you so much, and that's it for today's class. We're going to have a quiz. The online students are going to have their online quiz, but we're going to have a quiz now.